All right. So we are here for the second part of the discussion on how to construct wormhole states in loop quantum gravity with Luigi uh, Teixeira. Is that right? Is that how I say your last name? Yes.
Teixeira.
Te
Teixeira.
Teixeira.
Yeah.
Teixeira. Okay. Teixeira. All right. So in yesterday's session, we talked about three things. We talked about um, the spinor momentum formalism, the Grassmannian symmetry of n-particle massless scattering amplitudes, and the construction of harmonic oscillator coherent states. Okay. So all of those are fine with you, Luigi? Any questions?
No.
Okay. So now we come to this construction of generalized coherent states, right? So we have this A and A dagger, which is the annihilation creation operators. And to build the displacement operator, we exponentiate an element of this algebra, basically, right? And just in case anybody may not know this, an algebra, what is an algebra? Do you know what an algebra is, Luigi? The technical definition?
Vector space with multiplication.
Luigi knows. Okay, he's no amateur. Okay, so it's an algebra, and so now we can take any Lie algebra and uh, exponentiate it. Well, it can any Lie algebra, semi-simple Lie algebra with generators can be written in terms of copies of SU2. So this is the important thing, because basically it says that you can take any uh, semi-simple Lie algebra, which describes the vast majority of symmetries we consider in physics, and treat those systems in terms of copies of SU2. And you can map SU2 to the harmonic oscillator. So you can construct displacement operators in an analogous manner. But now the difference is that uh, if you have n sets of harmonic oscillators, you need a complex number for each set. Right? So basically, it's like taking n harmonic oscillators and constructing a coherent state for n harmonic oscillators. So your phase space now will be 2n dimensional, right?
Mhm.
And for each harmonic oscillator, you need a single complex variable, complex number. And for n such particles, you need n complex numbers, right? So we can construct a displacement operator in this way. And these are what we call generalized coherent states. Now, while you can do this formally, right, it's also important to check that these parameters alpha, do they actually correspond to a point in some classical phase space? Right. So in the harmonic oscillator, in the normal case, fine, we know that they do. Right. So when that is why this spinorial formalism of LQG is necessary. In the spinorial formalism, this correspondence exists between these n complex numbers and a point in the classical phase space of loop quantum gravity. So we're going to use these to construct these intertwiner coherent states, right? And Luigi, of course, knows what intertwiners are, but just to, for the sake of completeness, intertwiners are these states of loop quantum gravity which correspond to vertex in a vertex in a spin network graph. And sorry about that. And great. So we need these ingredients: a Lie algebra, a set of complex numbers, which parameterizes the classical phase space. In LQG, both are present. How do we get these? So if you consider a set of n-valent vertices or a single n-valent vertex, so basically a vertex with n edges coming into it, and you look at the algebra of operators which you can define on that Hilbert space, right? So each edge is basically labeled by a copy of a representation of SU2, a J label. So associated with each edge of that vertex, you have a harmonic oscillator in some spin J representation, right? And when you and then there are commutation relations between the operators, and these are the triad operators, right? Because the triad operators correspond to this angular momentum algebra. And there are non-trivial commutation relationship between adjacent pairs of edges. And so when you calculate it, you find that you get a certain Lie algebra, and that Lie algebra happens to be the Lie algebra of the n-dimensional unitary group. And you can also show that there is a classical phase space associated with this geometry, right? So Luigi, you probably might remember that when we talk about canonical quantization in LQG, we go from metric to connection variables. So, and then in the connection variable approach, our degrees of freedom become these one-dimensional holonomies living along
Yes.
edges, right? So one can actually construct a classical phase space associated with those holonomies, and the construction is a little bit quite elaborate. So it's not important though for our purposes. But that classical phase space is labeled by n complex numbers. So that's because so for each edge you have a single complex number. And what that physically corresponds to, physically it can be interpreted. So sorry, not a single complex number, but a spinor, an element of C2 living on each edge, right? And so physically what that corresponds to is a null momentum living on each edge. Because if you remember from yesterday's discussion, right? Spinors, there's a one-to-one correspondence. And now to construct this Lie algebra, we need what is called the Schwinger-Boson construction. So the Schwinger-Boson mapping basically is a map which takes you from the harmonic oscillator to the SU2 rotor, to the angular momentum algebra. Okay, and so how does that work? And again, yeah, these classical labels are defined only when you work in the Spinorial formalism. So here is okay. So we've talked about generalized coherent states, and then I talked about what are the requirements and why they are already present in LQG. And now I'll talk about Spinorial LQG. Okay. So this is the classical phase space of Spinorial of loop quantum gravity. Okay, and the variables live on edges. Degrees of freedom live on edges, right? So there is a holonomy and a flux x associated with each edge, right? The holonomy corresponds to the connection. The flux corresponds to the triad. Right.
Right.
And these objects, so the holonomy is an element of SU2, it's the group
The group and the flux
and
element of the algebra.
of the algebra. And if you take the group SU2 and you ask what is the tangent space of SU2 at any point, right? The tangent space is the Lie algebra, the derivation on the group.
Yeah, usually the algebra is defined as the identity, but I guess you can, since it's a left invariant vector field, you can parallel transport.
You can, right? So if you take any manifold and you take the set of all the tangent spaces at each point, right?
You get the
That becomes
tangents bundle.
the tangent bundle, fiber bundle. That's what it is.
Yeah.
Right. So this lives in the tangent bundle of SU2.
Mm-hmm.
And then the Hilbert space becomes the space of square integrable functions on SU2.
Mm-hmm.
Okay. Now, but this is not adequate for our purposes. We need to again change to
Change
again change our
gears.
variables. Yes. So instead of this, so there is an equivalent representation of this same data in terms of a pair of spinors, here written as Z and Z tilde.
Mm-hmm.
Right. So again, the logical progression, you start with the ADM metric variables, go to the ADM connection variables, then you quantize on graph states, or even before quantization, you use graph states to define your classical degrees of freedom living on those states. And those degrees of freedom are labeled by holonomies and
Fluxes.
Fluxes.
And fluxes.
Right. And those holonomies and fluxes are then equivalent, have an equivalent description in terms of spinors. So it seems like a rather convoluted and a very but at each step one can show that the physics in the previous step is encoded in what is coming next.
Yeah, you have the same degrees of freedom.
Right? Yeah.
SU2 has 3 degrees of freedom. Each spinor has basically 3 degrees of freedom.
Right. Exactly. So
spinors are rotation objects after all.
Right. I mean, they are all, SL2C acts on the on those spinors, right?
Yep.
Or is it SU2? SU2, sorry.
SL2C.
SL2C, okay. So now
It's
we can
SL2C.
construct, right. Now we can construct, so what is the interpretation of these spinors? Each spinor is attached to one end of an edge. And you can take this bracket of the spinor with the
all the matrices.
Yeah, and you can get back 3-dimensional vectors, right? I mean, this is the same thing, but in reverse.
Yep.
Going from 3-dimensional vectors to SU2 is the reverse of that.
Yep.
And you can get a pair of vectors like this, X and Y. And this X and Y has a very, very beautiful and a very, very simple physical interpretation, geometric interpretation, which is that you can view this X. So each edge is attached to some face. Right? Or is it you can, I mean, you can think of some surface which is pierced by the edge.
Yes.
And when it pierces that edge, it gives that surface some area.
Yep.
So this X and Y are the normals to that surface. And they satisfy this relationship, which one can show by
the normals at the point of intersection.
At the point of intersection, yes.
Okay.
Okay. And then there is this one last equality, which you can show by using the
Pauli
SU2
matrices.
relations.
Yeah.
Pauli matrices.
Yeah.
And what it's not just that these are normals, it's that these vectors, they encode the area of that face. Okay.
Yes.
So because the vector has two aspects, one is the magnitude, the other is the direction.
Yep.
So if you take any two-dimensional surface, right, and you ask me to characterize it, I will say, okay, it has an area and there's a normal vector to it.
Yep. In 3 dimensions, you
Together,
have that. Yes.
right? A two-dimensional surface embedded in a three-dimensional space. This is important.
Yes. Yes. Yes.
So these are each of these three vectors represents a area. And this is the picture, physical picture. Maybe I should show this physical picture in the beginning. Right? And this is the classic, these vectors are the classical counterpart of angular momenta. So when you quantize it, you will get
Spin.
SU2, yes, spin. Right? But now here's the one thing, right? Imagine you are building up geometry by taking these edges and these faces, right? So you want to be able to glue the faces together in some way, right?
Yeah.
So in order to glue them, there has to be some matching condition which is satisfied, right? One matching condition is that the area should be the same.
Okay.
Because if the area is not the same, you can't glue them together, right? It's like in a tiling, if you have tiles, if you have two tiles and you want to put them together, right? I mean, you could have a more complicated situation where you have two surfaces which add up to the same area as this surface and glue it like that also. But this is the simplest case.
Okay. Okay.
That the areas must match. Okay. Right. You could think of either one or both of these surfaces as being a composite surface, being constructed of other quanta of area also. But the point is to glue them together, the area needs to match.
Okay.
Right. Now, one might say that that is not sufficient. You also need matching between like the shape of the surfaces, but we are not going to get into that. Right. So we started with this pair of spinners on each edge. And then we can construct these three-dimensional vectors. And this is just to show that you can reconstruct the holonomy and flux variables from the spinners.
I'm not familiar with the square brackets.
Yes, the notation. So that's coming up next.
Okay.
So let me just mention what the spinner notation is, right? These are the ordinary spinners, the bra and get relation.
Oh, it's a dual spinner. Okay.
The dual spinner, yes.
Okay.
And then in terms of these dual spinners, you can construct these spinner bilinears and a spinner outer product and this. Okay. So let me just go back here. So, but the space of these of C2 cross C2 is bigger than the tangent space. So because there is some gauge degree of freedom which is there. The gauge degree of freedom comes from the fact that that you can take these spinners and multiply them by an arbitrary complex number, and that will not change your
by an arbitrary
the expression
phase,
for
right? by an arbitrary phase, right? The
By an
magnitude
arbitrary
would change.
phase. Yes. By
Yeah,
an arbitrary phase. Yes.
magnitude would change if the
Yes.
complex number is not unitary.
Yes. Right. That's why it's U1.
Yep.
And this is a double quotient, meaning that it has to, it has to satisfy both at the level of what do you call it? The variables themselves, and also that the constraint, this area matching constraint, which is this x square minus y square in the second line.
Mm-hmm.
So that selects a physical sector. It should satisfy that also. So that's why there's a double quotient.
Okay.
All right. So this is the Spinor notation. And one very useful identity is the last one, which shows that if you take the norm squared of the vector,
Flux
which is the inner
variable,
product,
you get twice the area. Okay.
twice the area, right? And where does the angular momentum come in? That you can see in the second last row, when you write down the outer product of the spinor, when you write it as a matrix, you can write it in this way. So you get this J, and that J will turn out to be our angular momentum. Now, right. So now we come to this. Where does this? What is this UN intertwiner algebra? So now we're going to talk about the quantum state space for an n-valent vertex, right? So for a single vertex, it's the usual, we know L square integrable functions on SU2. For n faces, it is n holonomies. Then we can Fourier transform using the Peter-Weyl theorem, right, to go to the momentum space on the group manifold. Right, so the group manifold is like the position space, the momentum space is like these Wigner matrices. So these are the Wigner matrices, and these Wigner matrices can be viewed in this way, right? And this construction, I think I showed you once before, but in case you might not remember, I can remind you. Right. But we can come back to this a little bit later. So, but the bottom line is that on each edge, there are two copies of a spin J particle. But that's the same statement that you know, right? So now the picture that we have is the following. This is a polyhedron, right?
Yes.
And all of these edges are coming in, and we want what makes it a polyhedron is the fact that all the faces must match together. There should not be any gaps.
Yes.
Right. So there is something called Minkowski's theorem, which says that if you give me a set of n vectors in three-dimensional space, any set of three vectors, I can always construct a unique polyhedron which corresponds to that set of vectors, as long as that set of vectors adds up to 0.
Okay.
The sum of those vectors should be 0, right? So that, in terms of scattering, that corresponds to conservation of angle of momentum.
Yeah.
Right. So now we know that the basic degrees of freedom living on these edges are angular momentum, angular momenta. And we want to write down coherent states for angular momenta. So how do we do that? We can, this is the Schwinger-Boson transformation. You can take any so here JZ, J plus minus are the usual SU2 generators or operators, and A and B are harmonic oscillator ladder operators, but you need two of them. You need a set, a pair of them. One, so we call one A, the other B. So now in this representation, with each edge we have associated, we have a pair of harmonic oscillators.
Okay.
Okay. So for instance, you can construct a Fock space associated with this, with each face, right? This is for each face. The vacuum state is just 0, 0. And, you can act on it with A dagger n A times and with B dagger NB times. And so you construct basically a state that has a certain number of excitations of the first kind and certain number of the second kind. Right? But again, we have to keep in mind that all of this corresponds to geometry. Right? So the J's give us this area, right?
Yes.
So how is the area encoded in this picture? It is encoded in this way. You can define you have the normal number operator or the Hamiltonian for each harmonic oscillator, A dagger A and B dagger B. And so the average of those, you can call the Hamiltonian associated with each phase.
Okay.
Right? I mean, this is, well, there's an extra factor of 1/2, but otherwise this is just the harmonic oscillator energy, right? And then you can check using the relations given at the beginning, the Schwinger-Boson relations, that this operator E, it satisfies this identity given in the last column, in the last row, last line, that J square is equal to this.
Okay.
I mean, there's a lot to digest, I guess.
Yeah.
And maybe I could make the presentation streamlined in it and make it simpler.
Yeah, I'm following.
Right. And now what is this J square? J square gives you the area. And so what is the relationship between this harmonic oscillator Fock space and the angular momentum state space? Right? NA and NB label the harmonic oscillator excited states. Right? But the rotor, the SU2 state space, it's labeled by J, whatever J is for each given edge, right? And also the M, the magnetic quantum number, right? And the magnetic quantum number takes values from -J to +J in steps of 1, right? The usual quantization of SU2. Right? So if J is equal to 1/2, you have two states corresponding to upspin and downspin. M is equal to plus half and minus half.
Yeah.
Right? And so on. So you can show that there is a one-to-one correspondence between this harmonic oscillator excited state and this angular momentum state. And so you can see if you start with some j, let's say j is equal to 2, right? Then what is your spectrum? Your spectrum is m is equal to -2, -1, 0, 1, and 2, right? So you can think of the state 2, -2 as your ground state. Just the same way that you can think of a downspin as your lower energy state, and then a magnetic field acts on it and flips it and gives you an excited state. So this is the lowest weight state in language of Lie algebra and whatever. This is called j, minus j, that is the lowest weight state, and j, j is the highest weight state. So you can treat the lowest weight state as your vacuum, right? And then each time you act on this vacuum with this j plus operator, right, you go up by one step. Right? But you cannot go beyond m is equal to plus j. The number of states in the in the spectrum of the oscillator is finite. Not oscillator, sorry, of the rotor is finite. Right? So SU2, there is a finite number of states, right? If j is equal to half, you have two-dimensional Hilbert space and so on, right? If j is equal to 1, you have a three-dimensional Hilbert space.
Yeah.
But the state space of the harmonic oscillator is infinite dimensional. Because NA and NB can be anything. So in order for this mapping to make sense, you have to impose some constraints on what the allowed values of NA and NB are.
Okay.
And so the picture is that NA and NB, the sum of NA and NB is equal to J, and the difference is equal to the magnetic quantum number.
Okay.
So one way to think about it, like imagine this, that you have an, let's say J is equal to 2 once again, okay? Right? Then what are the allowed values of NA and NB? I think, do I have that? No, I don't have that. So the allowed values of NA and NB, right? The maximum possible value of NA can be 4, and the minimum value of NB can be 0. Alternatively, NB can be 4 and NA can be 0. Right?
Oh, right.
Okay. Or 3, 1, or 2, 2, or 1, 3. Right? So it's like you have these oscillators. The total energy corresponds to the area. So if you change the energy of one oscillator, decrease it, and increase the energy of the other oscillator, you are not changing the total energy.
Yeah, the total spin has to be 2 because we are working with gravity.
No. It's not related to that. It's not related to spin 2 as in gravity. This J labels the SU2 representation, right? We are working in the spin network formalism, right? So in the spin network formalism, you have a J label on each spin network edge.
I see.
So
you
for
just
now,
picked
this
you just picked an example with j equals to 2.
I just picked an example. That's right. Yeah.
I see. Okay.
Right. So if you have j is equal to 3, you can go from 6 and 0,
I
then
see.
5 and 1, then 4 and 2, then 3 and
3 and
3, then 2
3.
and 4, 1 and 5, and 0 and 6.
I see. Okay.
So the total area remains a constant, right, between these oscillators, the total energy.
Mm-hmm.
But the difference in energy keeps changing, right, as you go from this state to this state.
Mm-hmm.
That difference in the energy represents the overall magnetic quantum number.
Mm-hmm.
So here, let's say the difference is positive and maximum. You come down, 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 and then it becomes negative and maximum. So it's like taking a spin and then, bringing it down in as many steps as needed,
Okay.
right?
Mm-hmm.
So if j is equal to 2, you start with the m is equal to 2 state. Then you come down to m is equal to 1, then 0, then -1, then -2. You must have seen that diagram in quantum mechanics textbooks, right?
Mm-hmm.
Which shows these vectors.
Yeah.
So this is a constraint which has to be imposed on that Fock space. Okay, so that's a lot to take in, right? And I hope that you're not getting too tired of listening to me. So shall I stop here, or shall I let,
You can continue.
let me just tell you about the construction of these operators EIJs.
Okay.
Okay. So this is really the brilliant insight of Friedel and Levine, right? Is that first of all, you take these edges corresponding to spin networks, then you map them to the harmonic oscillator algebra.
Mm.
When you map them to the harmonic oscillator algebra, you get a pair of oscillators on each edge. And now to
Okay.
construct the Hilbert space of n edges, right, you need to consider interactions between the edges.
Mm.
So what will be the total Hamiltonian? Like if you have a system of n harmonic oscillators, the total Hamiltonian operator will look something like this. Well, sorry, not the total Hamiltonian, the interaction term.
Mm-hmm.
So if you look at this, you have this E.
I expected interaction to mix A and B. No?
No, of course. Otherwise, there is no interact. No, it's not mixing A and B. It's mixing A and B and B.
Well,
AI, see, you have AI dagger AJ and BI dagger BJ.
yes. But weren't they? No, they weren't mixed, right?
Well,
It were same numbers. Now you are mixing different labels.
when you construct the SU2 algebra for a single edge, you have this
Oh,
J plus and J
okay.
minus.
You are interacting different A's and different B's together. Okay. But say A and
Right,
B shouldn't mix.
right.
Why doesn't A and B mix?
No, it does mix. That's what I'm trying to tell you.
Hmm.
That's what I'm trying to tell you. This is my daughter. She's calling
Okay.
to show me to show me something. So I guess she can also be a part of the YouTube video. Say hi. Hi bolo, Seanchi. Hi.
Hi, hi.
This, ये दिख रहा है तुम्हें? इनका फेस दिख रहा? अभी एक सेकेंड.
Showing her the works. for her to be
हाँ ये
on
दिख रहा है इनका
on
फेस?
par.
हाँ, ये बड़े भाई हैं तुम्हारे। इनके साथ मैं रिसर्च कर रहा हूँ। हम्म। So Luigi, say hi. This is my daughter Sayanshi. I've just
Hello.
made you her. I have just made you her big brother because I didn't want to make you feel too old by making you her uncle. Uh, though I suppose you could be. So
Well, I kind of
anyway,
have enough age for that.
exactly. So ठीक है. I'll call you back. Okay, after I'm done. All right. So coming back to you and coherent states. Um, you have this right. So now you see what is going on, sort of. This is a
Yes.
single edge. This is for a single edge,
Mm-hmm.
and then we introduce these operators. So and you have studied the tight binding Hamiltonian in many body physics.
What?
In condensed matter, right? When you want to
Mm.
describe like a conductor or an insulator or material like that,
Mm-hmm.
right? You say that there is an electron, there is a lattice,
Yes.
and you can have on each lattice site you can have one or more electrons or zero electrons,
Mm-hmm.
right? And these electrons can hop from one lattice site to another lattice site, right?
Yeah.
And that hopping, how do you describe it, right? You describe it in terms of creation and annihilation operators.
Okay, makes sense.
So this first term, for instance, AI dagger AJ, right?
Mm.
It's a hopping term which is destroying an excitation on the jth phase and creating an excitation on the ith phase.
Yes.
So it's like you have two faces. The area of this face is shrinking, or the
Oh,
A area of this face is
okay.
shrinking, and the area
No,
of this face is growing.
no, yeah, I understood. We are interacting the the A oscillation on one phase with the A oscillation on another phase,
Right. So
but
the
then
area,
we do not mix B and A in this sense.
no, or at least not yet.
Okay,
Not yet.
B and A
They do
are
get mixed.
unrelated
They do get
in the
mixed.
moment. I
Yeah,
see.
not
Okay.
yet, but they do get mixed. So it's like imagine your polyhedron surface is like an electron gas,
Mm-hmm.
and the local electron density measures your area, so to speak.
Mm-hmm.
And then the density can fluctuate.
Yeah.
Electrons can flow from one part to another part, and so this part becomes smaller in area, this part becomes bigger in area, so to speak.
Yeah.
So this picture is actually very nice because it also gives you a reason for why states corresponding to spherical geometry should be preferred, or some sort of symmetric states will be preferred,
Mm.
for the simple reason that, if you again think of this as an electron gas, the equilibrium configuration is when there is a uniform distribution.
Minimizes the area.
Not just minimizes the area, but minimizes the fluctuations of area around.
Yeah.
If you have a little fluctuation here, it will propagate and flow away, just like in a conductor.
Mm-hmm. Okay, makes sense.
So and so then you have a hopping term for the A and a hopping term for the B.
Mm-hmm.
And these operators have a certain commutational algebra, which happens to be the same as the geometry
UN.
group. Yes. So it's a pretty long process to come to this point.
Mm.
And what is the nice thing about these operators? Why are these operators nice, right? like you can construct lots and different kinds of operators, right? But these are, I mean, you want to you have this Gauss constraint, right? The Gauss constraint is basically saying that the sum of all the angular momenta adds up to 0. Without the Gauss constraint, you don't have a closed surface.
Yeah.
You have an open surface. So if these operators did not commute with the Gauss constraint, right, then they would take you out of the physical space, physical state space. Or
when you if it does not commutes, then when you excited one phase from the other, it would open the polyhedra.
yes, that's right. The polyhedron would not remain closed.
Yeah, it would open. Okay.
Yeah. That's what makes these useful. And now we come to this other set of operators.
Oh, okay.
Which, you were afraid might show up, and they do. So now these are, because again, it makes sense. You have these two harmonic oscillators, but why should they not interact with each other?
Yeah.
After all, if you go back to the Schwinger-Boson representation, you can see that I told you, right? The J and M, the way it works is that A decreases and B increases on a single phase, right?
Yeah.
So it should be possible for that to happen on different phases also. That means A on one phase decreases and the B on a different phase
increases. Yes.
Right. I mean, you could have such.
Yeah, as long as the total of the polyhedral remains constant.
The total area remains constant and the closure is maintained.
Yeah.
Right. So these are also operators which you can construct. Now, what kind of operators are these? Fij.
You have products of annihilation of both
Right.
oscillators.
So they are annihilation operators.
Yes.
And what can we do with annihilation operators?
Lower the oscillations.
No. That is true. But like, what are we trying to do with all of this? What is our motivation for talking about all of this? What kind of states are we trying to build?
Coherent states.
Coherent states. And what do annihilation operators do?
They coherence. What? I can't recall right now. I have a blank.
Let me just go back. The coherent states are the eigenstates of the harmonic of the annihilation operator.
Oh yeah, that's right. So
and the
we
displacement
created that's annihilation operator, so we can get the mixed coherent states.
That's right.
I see.
It's not completely straightforward like this but it's close. So, but you see, that's what we have basically done is we have constructed a harmonic oscillator representation of the polyhedron Hilbert space. And using this harmonic oscillator representation, we can now construct coherent states. And this is how we construct these coherent states. So if you take the this thing Hermitian conjugate, you get a creation operator, right?
Why is the bracket curved now, not angular anymore?
That's just to indicate that the fact that we are talking about a state of the whole polyhedron, I think.
Okay.
Yeah, because it's the Fock vacuum of the whole this thing.
Okay.
Now, but you can see that there is one new ingredient that has crept into this discussion, which is this z variable or the z variable. You can see it's written as f of z, right? There's a f of z. And if you go back to the last slide, here f, there is no z. It's just f.
Yes, Fij.
So what is this z? Why did this z creep into the, why did it crash the party?
Z gives the it labels the ij because each oscillator can be matched with a spinor, right? So and then
So
you
to
have
cons
this inner product of spinor draw spinor, which should give you that product. It's an invariant. It's an SL2C invariant, right?
Oh, okay, let me interrupt your chain of thought because, so again, what are we trying to do here? What's the big picture?
Coherent states.
Coherent states. For coherent states, what do you need?
You need annihilation operators. You need
Annihilation operator and something else?
unexcited states for each shocks.
No. Again, let me go back to the harmonic oscillator coherent state. You have the A, right?
Oh,
A hat.
you need an eigenstate of the annihilation operator.
And those eigenstates are labeled by
The eigenvalue, which is
by the
which will
complex
be
by a complex number.
by a complex number which encodes the expectation value of position and momentum.
Right, which encodes this thing, the 1 second. Switch out my, right? So to describe the coherent state, you need two things. You need the annihilation operator and you need the this thing. You need these complex numbers. And these complex numbers should correspond to the classical phase space of something.
Oh, thatCijs are the complex numbers corresponding to combinations of the oscillators.
That to the classical phase space.
To the classical phase space, yes. Okay.
Now you
see.
You see the thing, the picture come into,
right?
right?
The picture coming together, yes.
Exactly. So you have to go through all of this. It's a little bit like Lord of the Rings, you have to like slog through all of Mordor. And seriously, reading Friedel, Speziale and Levine's papers is not easy. I tell you that. I've read a lot of papers in my life, and those are some of the most dense mathematics I've ever read.
I see.
And if it wasn't for one of my students like you, who was working with me on a project, I would never have had the courage to do it. So it's this Suresh, you can see the name, right? Suresh, it's a girl, Devadarshini Suresh.
I see.
So we have these annihilation operators, but to label the coherent states, we will need these complex numbers, these Z labels.
Yes.
And for each phase, we will have a single spinor, a single Z. Because each edge, there are two Zs, but this Z lives on this end and this Z lives on this end.
Okay.
So for a single polyhedron, for each phase, we have a single spinor.
Yes.
And so we take a linear combination of these spinorial variables. Well, you need to take some mixture of the i's and j's, in this way and construct this Zij matrix.
Mm-hmm.
And then you need to contract the Zij matrix with the Fij matrix to get your Fz.
FZ. I see.
And then when you act on the vacuum state with this Fz, so what is the interpretation of this object here?
This is an object that have a given total angular momentum, which should be 0. No.
Total given area.
Given area. Oh yeah, the J gives the area, right? Yeah. Given area, and the Z should give the punctures, the directions of puncture. The momentum.
I like to think of it in terms of momentum, in terms of scattering.
Okay. Z gives the scattering momentum.
And so you have this Gauss constraint, right? That Gauss constraint basically corresponds to conservation of momentum.
Mm-hmm.
Right?
Right.
So these are the coherent states. We have finally constructed the coherent states. And this did not involve taking an exponentiation, though you can show that you can exponentiate also and get something similar.
Okay.
And these states are indeed minimum uncertainty states.
Mm-hmm.
So you have these operators Eij, right? Which what does it measure? It measures the fluctuation of the area.
I see.
Between
pairs
of faces.
Yes.
And so the fluctuation of this operator goes as 1 over root of J, where J is the total area.
When the area is large, the uncertainty is minimum. Yeah, makes sense. Classical units.
It goes lower and lower.
Although it doesn't, it takes a while to vanish, right? 1 over square roots. It takes a while to vanish.
Well, no, I mean, what's the smallest possible value of J? The smallest closed polyhedron you can construct is a tetrahedron. Right? So for that, J would be like 1/2, 1/2, 1/2, 1/2. If you take the smallest representations of each edge, the smallest angular momentum, you would get a total area of 2.
Okay.
Right?
So you have 1 over square root 2.
Yeah. So that's pretty large, but that's to be expected because you're talking about the smallest possible quantum of volume, quantum of geometry. Right? But as you go up to higher values of J, it decreases.
Oh, yeah, I see it decreases, but it doesn't decrease that rapidly.
Yes,
1 over square root is a fairly slow decreasing function.
Yeah, you're right. It is not that this rate of decrease will definitely affect some physical properties, which I can't think of right now. But yeah, it will be important. Okay.
Okay.
But the main point is that it does decrease.
Yes.
Now, these coherent states, they have a symmetry. Remember that these Z variables had this Grassmannian symmetry, right? When we talked about the momentum spinors.
Yes.
So we can apply that same Grassmannian symmetry to these states. Right?
The point is that, again, you can take some observer and do a Lorentz transformation of that observer. Boost that
Yes.
observer, whatever, rotate it. According to that observer, the polyhedron the shape will change, right?
Mm-hmm.
The area normals will change. Some will
Yes.
contract, some will, rotate.
Mm-hmm.
But the sum, again, they must continue to satisfy the closure constraint.
Yes.
Because performing a Lorentz transformation on an observer should not cause this polyhedron to fall apart, right?
Yes, I agree. The
Right?
polyhedron should remain, although skewed, it should remain
right,
whole.
right. So the total area remains the same, but the shape changes.
Yes.
And that shape is given by this configuration of spinors, Zi spinors.
Mm-hmm.
And if you remember, these spinors, they correspond to a point on the Grassmannian.
Yes.
So these coherent states inherit that Grassmannian geometry.
Mm-hmm.
Meaning this. So now you can take you can take, well, you have to be a little bit careful about how you do these things. So you can take any of these spinors and multiply it by
L2C matrix.
L2C matrix. And if you do that, how does your coherent state transform? It picks up a factor of determinant of lambda to the power j.
Okay.
Right? So if lambda is an SL2C, then determinant is
1 and the coherent state doesn't change.
right.
Okay.
So these are the coherent states of quantum geometry, and they have this Grassmannian symmetry.
Okay.
All of this, by the way, was known and done by Friedel, Speziale, and Levine in 2006, 8, and so on.
Mm-hmm.
What is my contribution? My contribution is the realization that this has an equivalent description in terms of scattering amplitudes. So I'm not going to go into that right now, because I want to tell you now how we get the wormhole geometries.
Okay.
How do we get the wormhole geometries? Well, we have these polyhedra.
Mm-hmm.
We take another copy.
You entangle to polyhedra.
You entangle to polyhedra and construct a thermofield double state, and boom, you get a wormhole.
Makes sense.
Right? And so this would be a bona fide construction in loop quantum gravity, right? Which is making direct contact with all of the work that has been done under the alleged title of string theory. I mean, I say alleged because they're all working with ADS CFT, which originated in string theory, but it doesn't need string theory for its justification.
Yeah,
we know that.
ADS CFT has kind of transcended string theory at this point.
Exactly. So we have a construction of, we have a holography in LQG
Mhm.
and wormhole geometries in LQG. Da-dum. I mean,
There we have it.
it's still work in progress, but
Mhm.
all of the ingredients are there,
I see.
right? So I'll stop the recording at this point, and then we'll talk about more top secret details.
Okay.
Okay. All right.